All right, welcome to the videos for exam 2. This is the start of those sections. So section 5.3. This would be, what are we up to, homework 4. So properties of rational functions. And obviously you need to know a few things like what is a rational function and what questions are associated with rational functions. So polynomials were pretty, boring in terms of their domain and range. The domain of a rational function is a little more interesting because it does involve, so I'm going to adjust the camera here, it does involve division, so there's something we need to think about here. So domain of a rational function, vertical asymptotes of a rational function. Asymptotes, very important topic, but their importance are beyond just finding the asymptote, so I'll touch on that. And then you may have asymptotes in two categories: vertical, and then what we call horizontal or oblique asymptotes. And obviously you want to be able to find those. All right. So one thing I'll say it right now. So asymptotes, and the one graph that everybody should know that has an asymptote in it is y equals 1 over x. Goes through 0.11, and the x-axis and the y-axis act as the asymptotes. Should be a curve. All right. So, and this is an example of a very simple example of a rational function. But the asymptote isn't just this thing that you're forced to draw. It also tells us how the graph leaves the box. In other words, it allows us to visualize what happens a mile outside this box. This graph is just getting closer and closer and closer to the x-axis in both directions. If all you do is focus on what's going on inside the box, you're missing half the story. So I don't know if that thought is developed in this class, because they pepper us with very specific questions like the equation of the x-axis is y equals 0, and they'll ask us what's the equation of the horizontal asymptote. Here it is, horizontal asymptote. The reason why it's here is it's a very important idea moving forward, a huge idea moving forward in calculus classes and such. All right, so the explanation is you have two polynomial functions, one in the numerator and one in the denominator, and that is a rational function. And of course, the denominator equaling 0 would be what you exclude from the domain through reasons we've already discussed. All right. So we look at this. By the way, range, they're not talking about it yet. It's a more complicated idea. They're just talking about domain right now. Polynomial over a polynomial. And if you set the denominator equal to 0, you'll see where you're dividing by 0. So it is a rational function, and we know its domain. Rational function. By the way, 1 is a polynomial of degree 0, but it's a polynomial. It's considered a polynomial. And in its factored form, if you set the denominator equal to 0, you can see that as well. By the way, we are going to be interested in degree. So degree 3, degree 2, but what's different about this one is that x squared plus 1 equals 0 has no solutions. So the denominator is never equal to 0. A quick sketch will verify that. There's a graph of x squared plus 1, and it never crosses the x-axis. So if the denominator can never be 0, this is an example where the domain is the set of all real numbers. I'm a little concerned about this example because personally I wouldn't say it's a rational function. And the reason why I say that is once we simplify it, get rid of that 2, by factoring, we just get a linear function, meaning it's a function without a denominator. And so we saw earlier that 1 over something like x squared plus 5 is a rational function. But x squared plus 5 over 1 would not be considered a rational function. So ones are allowed in the numerator, but not the denominator. So what I mean by that is, I don't really consider this a rational function. It's a linear function. But they are correct that out of respect for the equal sign, or in other words, out of respect for where this came from, it would be appropriate to say that x is not equal to 2. Not by looking here, but by looking at the very beginning. So they didn't say anything wrong about this problem, but it's not a rational function. So funny example, but we'll see. All right. So what are the questions they could ask you about this? The domain, well, the denominator cannot equal 0, so x not equal to 0. By the way, sometimes when they talk about this, what they're talking about is the whole number line without 0 in it, which is 2 intervals. So they might have you write it this way. And what does that mean? The minimum is negative infinity, the maximum is 0 of this interval, and then there's a new interval that picks up right at 0 again. Minimum is 0, maximum is infinity. With the parentheses, it's the same as saying x is not equal to 0, but sometimes you can say it this way, and sometimes they want you to say it in the interval notation. All right, the graph has no y-intercept, and they haven't really taught you how to find the y-intercept yet. But to find the y-intercept, you set the function equal to 0. To find the y-intercept, you let x equal 0. And so that's a rule that we learned way back in chapter 1. You set x equal to 0. I don't know why I crossed that out. It was right. I just didn't have my arrow in there yet. You set x equal to 0, and what would happen? Well, you get 1 divided by 0. You get an error on your calculator. And if that happens, that means, there's no, mathematically, there's no y-intercept, right? Because x cannot equal 0. All right. The graph has no x-intercept. Again, this is kind of review, I guess, from, I don't know, chapter R maybe, or maybe it doesn't go that far back, but set the function equal to 0 and try to solve that. Well, if I cross multiply, I'll get 1 equals 0 literally, because x squared times 0. There's no solution to this, so there is no x-intercept. So what's our conclusion? If you have a function with no x-intercept, it's still going to be a function, meaning it's going to pass the vertical line test and maybe a few other things, but it can't cross the x or y axis or touch. Sorry, no intercepts. They are actually going to run a few more tests. They ran this familiar test where they put in h of minus x just to see if it gives you back what you started with. And if you remember that test, it's a test to see if a function is even or odd. You put in the minus, and if you get back where you started from, it's even. If I had gotten a minus sign right here, minus what I started with, it would have been odd. So if it's even, symmetry with respect to the y-axis. If there's a point here, it has a reflection point on the other side. Very typical thing to do. By the way, this idea right here, that they are picking the x values, and the author's trying to be clever or maybe even dramatic here. Most of us wouldn't pick 10,000 or whatever number that is. 10. That doesn't look right. Oh, square, yeah, that's right. 10,000, if you square it, you get 100 million. 100, you square that, you get 10,000. All right. So the author's picking some dramatic values here. I don't know if those are at all useful, really, in our graph. But there is a reason why the author's picking these fractions. And let's take a look at this. So the reason why the author's picking, this really small fraction and this really large fraction is he's trying to see what's going on outside the box. He's not really saying it that way, but that's what he's trying to do. He's trying to say, how does this graph leave the box? Once we study asymptotes a little better, we won't need these huge numbers, but think of what happens when you put in a big number. Look how small this is, 1 over 100 million. So that's so close to 0, most calculators might even give you 0, or change the scientific notation if you actually ran that calculation. So here's the graph without the ridiculous numbers, all right? Just with really these numbers and their reflected values. So A, B, and C, A prime, B prime, C prime. Remember, you could have put, it would have been fine to actually have put these numbers like -2 in the table, but the author's saying you can save time by saying, well, I know for every point here, because it's an even function, there's another point reflected over here. All right, so where's this 100, all right? So 100 is, way over here, but it's 1 over 10,000, so it's probably, indistinguishable from the x-axis itself right there. So what that means is this graph is getting closer and closer and closer to the x-axis, and it's not going to turn away from it abruptly. It's not going to cross it because there are no x-intercepts, and that's what we mean by an asymptote. In a physical class where I have students write their papers and such, draw these on their own, I tell them that exactly. The asymptote shows us how a graph leaves the box. Your graph should indicate this. So if there were a box here, I'd probably deduct a point for the author. Well, the box didn't really go this far, but in this illustration, but for the for a graph that stopped right there and didn't reach the edge of the box, because what's the asymptote there for? Is to show us what happens here outside the box. All right, I don't want to get too much on that because let's stick with what we're doing. Our job is to write the equations of the asymptotes when they ask us, and to pick the graph. The web, when I say pick the graph, the website doesn't have a graphing, has a few graphing systems, but it doesn't have a way of graphing something this complicated with an asymptote. So these are mostly multiple choice style questions. So pick the graph rather than graph the graph. All right, so this is a good question. Is this a rational function? Well, what if I told you rational numbers are in the form a over b? Right? Well, 1 over 2 is a rational number. But how about 1 over 2 plus 7? Is that a rational number? Like, it is, but we haven't written it that way. I'd have to actually add this together. It turns out if I add this together, I'll get a number over a number. So that's what's going on here. This is a rational function. It's just not written as a rational function yet, because rational functions are written as polynomial over polynomial. Turns out, however, this way of writing it takes advantage of that transformation of or translation of a graph that we kind of like. So while I could add this together and convince my brain that it's a rational function, I think we're better off just leaving it this way and thinking of this as 1 over, let me write this out, x minus h squared plus k. All I did was took my original graph and replaced h and k for these numbers here. Review the idea of translating functions if you're transformations and translating functions if you're not sure what I'm doing here. Anyhow, match this up. Do you see it? What am I subtracting from x? -1. What am I adding to the function? What am I adding to this function? -2. So my transformation is hk, or -1, -2, and let's see that in action. So I took this function, the original one, no numbers added. If I subtract 1 from x, it shifts the graph. If I subtract 2 here, it shifts the graph. It shifts the asymptotes by doing that. And we get this new graph. So here's the new graph, and it's just a shifted version of the first graph. This is what I mean by how the function leaves the box. When they say x approaches -infinity, they're saying what happens when the graph leaves the box from the left. And when they have x approaches infinity, they're saying what happens when the graph leaves the box to the right. Now with polynomials, there's only two possibilities. When the graph went right, it either left the box, up here at positive infinity, or it left the box negative infinity. But with rational functions, they behave quite differently. And for now, we're going to talk about those rational functions that leave the box with a horizontal asymptote. There's another way to leave the box. You can leave the box with a vertical asymptote, which we'll see as well. All right, so horizontal, for those who don't know the word, it's a line parallel to the x-axis. Vertical, line parallel to the y-axis. So here's an example of a graph leaving the box with a vertical line, x equals c. Here's another graph leaving the box with a vertical line, x equals c. In one case, positive infinity. In the other case, negative infinity. Leaving the box on the right with a horizontal line, and leaving the box on the left with a horizontal line. All right. All of those things are spelled out with this notation we don't really use a lot, with the arrows and the infinity symbols and lim, and but they're really getting into calculus ideas, as they should. We don't have calculus questions like these, but they're planting the seed of that. I'm just going to be happy that you can draw the graph and, I answer the questions they ask very specifically. All right, so I'd like to say this is probably one of the most, it's probably one of the most obvious things in the world of mathematics, but I don't know if students really see it that way. But how do you find asymptotes? So I'll go ahead and go through an example, but you have a polynomial over a polynomial. How do you find the asymptotes? We already know how to find the domain. You set this thing equal to 0. And if you set the denominator equal to 0, that will reveal the vertical asymptotes. Now there's also something called the non-vertical asymptote, horizontal asymptote. And that, I'm going to put an arrow right here at that line right there. You find the vertical asymptote by the non-vertical asymptote by dividing, sort of. Most people don't go through the physical division process, but that really is, what all it takes. And I call it the most obvious thing because if you asked a 7-year-old, what does that line mean when you have, P over Q, they'd say, well, that line means divide. So what should adults do when they have P over Q and they're looking for something? Well, divide. And if you get that, you'll always be able to find the asymptote. You can use a shorter trick, I suppose, but you can always do that. All right, so I'm not talking about division yet. I'm talking about vertical asymptotes. And vertical asymptotes just have you look in the denominator, and that's it. Now, of course, there's more to it. You have to reduce the fraction. If you reduce the fraction first, then that could change everything. But if the fraction's already reduced, the denominator reveals the vertical asymptote. Let's look at D and why it's different. So with D, this was the problem we were given, but notice how we had x minus 5 both in the numerator and denominator. What that means is at 5, there's just going to be a hole in the graph. A hole meaning is what we call it when we have a point that gets removed from the domain, but it no longer influences the actual graph we're interested in drawing. So there's only one asymptote that essentially survived, and so that just kind of goes over the idea of simplify first. Otherwise, you might, think that x equals 5 was a asymptote. Nope, there's a hole there. Wow, this looks so complicated. The most obvious thing in the world. I say obvious, I didn't say easy. I did say easy, but I shouldn't have. Finding the horizontal or the oblique asymptote. So Sudal is being very practical here. The other's not really having you do the division process. Well, sometimes you are, but basically the other's saying, okay, look at the exponents here. These are actually going to be real numbers when you see them. So look at the exponent, m for the n for the numerator and m for the denominator. And if the degree of the denominator is the big one, if the denominator is somehow bigger, what am I talking about? X cubed ... over x to the 5th ... You probably won't have numbers this big, but if the denominator has the bigger degree, y equals 0, or the x-intercept, x-axis, is the horizontal asymptote. So that's case 1. If they're equal, like 2x cubed over 7x cubed, right? If they're equal, you just grab these coefficients. Y equals 2 over 7. That's the horizontal line, 2 over 7. Remember, we're looking for horizontal asymptotes. And the last one that we're interested in, if the numerator is 1 more than the denominator. So let's say we had 3x squared plus 5x minus 9 over 7x plus 2, degree 2, degree 1. Top is 1 more than the bottom. In this case, you actually do long division, and again, that's not a surprise because That's a division symbol. And that will reveal the asymptote. That might be a surprise, but it will reveal the asymptote. We don't really have anything like this. They're saying, well, what if the degree is more than one power function? I'm just going to skip that one. All right. This is getting a little long. I'm going to take a break right now, and we'll pick it up with another video. So, but we're still in, what is it, 5.3.